Attention, dear viewers! We present an unusual episode, a kind of experiment, conducted for the very first time. Experienced listeners might immediately notice a difference in sound quality, perhaps reminiscent of a phone call. This is no accident, as the recording is being conducted remotely. Usually, episodes are created in the familiar studio environment, where we can see each other, exchange thoughts, and create together. However, circumstances this time are different, and the conversation is happening remotely, via telephone. Therefore, we apologize for any potential sound imperfections. Every effort has been made to provide interesting material and maintain the regularity of our releases. We hope that, despite the technical nuances, this episode will be enjoyable. Throughout a person's life, the sun appears unchanging. It seems as if it has always been this way and always will be. But this is a misconception. Like any star, our luminary has undergone a long evolutionary journey to appear in its current form, and an equally captivating future, full of astonishing transformations, awaits it. Welcome to the second part of our fascinating series dedicated to stellar evolution. This time, viewers will journey deep into stellar interiors to discover what causes stars to become dwarfs or, conversely, to swell to gigantic sizes, engulfing their own planets. You will learn how stars change their brightness and even their color, how they transform into mesmerizing planetary nebulae or explode as supernovae. And of course, we will discuss the fate of the Sun in 5 billion years. What awaits our star? A star's evolution depends on numerous factors. It's important to consider which generation it belongs to, its chemical composition, whether it has stellar relatives in a multiple system, and what caused the collapse of the molecular cloud that gave birth to it. However, the decisive parameter is its initial mass. This alone determines how a star will burn, for how long, and whether it will do so at all. Therefore, when astronomers compare stars and say one is larger than another, they almost always refer to mass, not physical size. The Sun is a star of moderate size. There are luminaries much smaller, known as dwarfs, and stars that are hundreds or even thousands of times larger. There are also tiny celestial bodies that began as stars but couldn't accumulate enough mass to initiate thermonuclear reactions. This happens if the initial mass is less than approximately 13 Jupiter masses, in which case a giant planet is born. If the protostar's mass falls between 13 and 80 Jupiter masses, a cosmic object with special properties emerges. At such a mass, gravity compresses the object's interior so intensely that the temperature rises to a level sufficient for deuterium, an isotope of hydrogen, to begin burning. By burning, we mean participation in thermonuclear fusion. If an object manages to accumulate 65 Jupiter masses, lithium also participates in the thermonuclear reactions. Deuterium and lithium engage in thermonuclear fusion at lower temperatures and pressures than other elements. Thus, there are objects in whose interiors thermonuclear fusion occurs, but they cannot be called stars. A cosmic body is considered a star only if nuclear fusion involves protium, i.e., ordinary hydrogen consisting exclusively of a single proton. Due to the low intensity and instability of their reactions, as well as their dimness, such objects have been named brown dwarfs. They belong to spectral classes M, L, T, and Y and are located in the lower right corner of the HR diagram, near red dwarfs. Although their existence was predicted in the 1960s, astronomers were only able to confirm the existence of brown dwarfs in the mid-1990s. Their low emission and insignificant size compared to full-fledged stars make their observation extremely challenging. However, thanks to advancements in astronomical observation, particularly the construction of telescopes with mirror diameters of 6 to 11 meters, thousands of brown dwarfs are now known. An interesting fact: they were initially called black dwarfs. But this name did not stick because astronomers predicted the existence of another type of object for which that name was more fitting. We will discuss them later. Don't miss the most interesting parts. After considering objects that are not stars, it is worth turning our attention to true luminaries, starting with the most modest representatives of the stellar kingdom. We are talking about red dwarfs, whose mass ranges from 7% to 60% of the Sun's. Unlike their brown counterparts, thermonuclear fire still smolders within red dwarfs, converting hydrogen into helium via the proton-proton reaction. There is no single consensus in the astronomical community regarding the precise boundaries of spectral classes attributed to red dwarfs. Most often, M-class stars are included, sometimes encompassing part of the K-class, although broader interpretations exist. According to scientists, red dwarfs dominate the stellar population of our galaxy. But their prevalence is not their only remarkable feature. They are also renowned for their phenomenal longevity. Theoretical calculations predict that red dwarfs can exist for up to 2.5 trillion years, which is 180 times the age of the universe. Thus, no red dwarf has yet exhausted its lifespan in the 13.8 billion years of the cosmos's existence. Moreover, it is believed that some of them may belong to the third, most ancient stellar generation, possibly being the first stars in the universe. Given that all known red dwarfs are still on the main sequence, scientists resort to computer modeling to peer into their future. Due to convective mixing of matter, helium does not accumulate in the core, which precludes the possibility of its further thermonuclear fusion. Convection also ensures the most complete burning of hydrogen compared to more massive stars. But sooner or later, hydrogen reserves are depleted, and the red dwarf enters the final stage of its evolution. Unlike the Sun, which is destined to become a red giant and possibly engulf Earth, red dwarfs end their journey differently, owing to their unique convective structure. Throughout its life, a star gradually increases its luminosity. This is linked to the growing concentration of helium in the core, which leads to increased pressure and temperature. In turn, this stimulates thermonuclear reactions and accelerates the burning of residual hydrogen. The released energy is emitted as photons. However, photons born within the star's interior cannot travel in a straight line due to immense pressure and density. They constantly collide with particles of matter, are absorbed, and re-emitted. Stellar matter is virtually opaque. Near the star's center, the mean free path of a photon is fractions of a millimeter. An analogy on Earth would be trying to illuminate a steel rail with a flashlight, where a photon would have to traverse a layer of matter tens of thousands of kilometers thick. Furthermore, red dwarfs have significantly greater average density than the Sun. It is with such incredible resistance that photons contend on their journey to freedom. But if one imagines a flashlight with a power of 10 to the power of 23 watts, such a light beam could penetrate the star's interior, being absorbed and re-emitted countless times. As a result of this long and complex journey, photons heat the star, most intensely its central region. Given that convection intensifies with increasing temperature difference, hotter matter rises to the surface ever faster. Thus, a red dwarf compensates for increased energy generation not by expanding, but by increasing its surface temperature. According to modern theories of stellar evolution, this process leads to an astonishing transformation. The red dwarf turns into a blue dwarf. Its mass remains small, only a few % of the Sun's, but its surface temperature reaches 8 to 9,000 Kelvin, corresponding to white-blue A-class stars. Sooner or later, the blue dwarf's hydrogen reserves also deplete. Thermonuclear reactions cease, and it begins to cool. As the temperature drops, the object reddens again, and then its emission shifts into the infrared range. This is how a red dwarf slowly transforms into a black dwarf, a star that changes its color for the last time and consists almost exclusively of helium. Of course, the theory presented remains hypothetical for now. To date, no blue dwarf has been discovered, which is explained by the colossal lifespan of red dwarfs from which they should form. The universe is still too young to reveal these exotic objects to observers. Another interesting category of stars is the so-called subdwarfs. Initially, this name was applied to stars of luminosity class 6, whose stellar magnitudes are 1.5 to 2 units fainter than main-sequence stars with similar surface temperatures. On the Hertzsprung-Russell (HR) diagram, they are located directly below main-sequence stars, forming a line parallel to it. These objects were initially called intermediate white dwarfs. But in 1939, Gerard Kuiper proposed the more concise term, subdwarfs. This group includes both white dwarfs and stars of lower mass. In general, the term subdwarfs encompasses two entirely different classes of stars, hot and cold sub-dwarfs. Despite the similarity in names, their origin, internal structure, and energy generation mechanisms differ significantly. Similar to main sequence stars, cold sub-dwarfs generate energy through hydrogen thermonuclear fusion. Their reduced luminosity is explained by a lower abundance of metals in their interiors. Such a chemical composition results in greater stellar transparency, facilitating the escape of photons to the surface. This, in turn, weakens radiation pressure, leading to the predominance of gravitational compression. As a result, the star contracts, and its temperature increases. Thus, despite the name, cold sub-dwarfs, they possess a somewhat higher temperature than stars of similar mass but with a rich metal content. Hot sub-dwarfs, in turn, belong to spectral classes O and B and are also known as extreme horizontal branch stars. They represent the late stages of massive star evolution, which will be discussed later. Progress in observational astronomy in the early 20th century, along with simplified access to observational results, significantly accelerated the development of astronomical science at that time. It was during this period that main sequence stars were classified, separated into a distinct group due to their characteristic position on the Hertzsprung-Russell diagram, which is also a product of that era. The diagram clearly shows a straight line extending from the lower right corner to the upper left. The main distinguishing feature of a main sequence star is the presence of hydrogen thermonuclear fusion reactions in its core, leading to the formation of helium. Main sequence stars include not only red dwarfs but also luminaries such as the Sun, Alpha Centauri, Sirius, and many other well-known stars. Main sequence stars can be divided into two groups: those with a mass less than 1.5 solar masses and those with a mass exceeding this threshold. This division is due to the dominance of the proton-proton cycle in the interiors of less massive stars and the CNO cycle in the interiors of more massive ones. Main sequence stars are in a state of hydrostatic equilibrium, where the energy released by thermonuclear reactions is balanced by gravitational compression. Thanks to this, the size and temperature of main sequence stars remain relatively stable. Since hydrogen thermonuclear fusion is the longest stage in a star's life, about 90% of all observed stars belong to the main sequence. At first glance, it might seem that larger stars, having a greater supply of hydrogen, should live longer, but this is not the case. With increasing mass, the rate of hydrogen burning increases disproportionately. In other words, doubling a star's mass also doubles its hydrogen reserves, but the rate of burning increases by 10 to 15 times. This is why the more massive a star is, the faster it exhausts its fuel. After this, it transforms into a supergiant, a red giant, or a white dwarf. A star's lifespan can vary from millions of years, imperceptible on a cosmic scale, to trillions of years in the case of stars with a mass less than 1/10 of the Sun's. The upper mass limit for main sequence stars is in the range of 120 to 200 solar masses. The so-called Eddington limit represents a theoretical threshold at which a star becomes so luminous that radiation pressure exceeds gravitational pressure, disrupting hydrostatic equilibrium. In this case, the star begins to lose mass, shedding its outer layers and thereby self-balancing. However, in reality, astronomers observe stars with masses significantly exceeding the Eddington limit, which indicates the incompleteness of our knowledge of the laws of nature. After a prolonged period of stability on the main sequence, the next stage of a star's evolution is the subgiant phase. This term, introduced into scientific use in the 1930s, describes a group of stars that occupy an intermediate position between main sequence stars and giants. The mechanism by which a star transitions from the main sequence to the subgiant stage can vary significantly depending on its mass. It should be emphasized that the terms subgiant and giant can be used not only to denote a specific stage of evolution, but also simply to characterize large main sequence stars belonging to spectral classes O and B. However, not all of them are subgiants in the evolutionary sense, and conversely, not all evolutionary subgiants belong to spectral classes O and B. In this context, subgiants are considered specifically as one of the stages of stellar evolution. As previously mentioned, stars with a mass less than 40% of the Sun's are fully convective. Throughout their life cycle, they burn almost their entire hydrogen supply, leaving behind only a helium core. Due to their small mass, helium burning never begins in them, and the star gradually cools, ending its existence. However, stars whose mass exceeds 40% of the Sun's undergo much more interesting metamorphoses at the end of their lives. It is important to note that, unlike red dwarfs, such luminaries no longer possess full convection. Energy from the core to the upper layers is primarily transferred by radiation. This means that helium, formed in the core during thermonuclear fusion, cannot be carried out by convective currents and remains trapped inside. Thus, for billions of years, while burning hydrogen, the star simultaneously accumulates helium in its core, which does not disappear. Over time, when hydrogen reserves in the core are completely exhausted, only a ball of helium plasma remains. The temperature and pressure within it are still insufficient to initiate further nuclear fusion reactions, and they cease. The star loses its source of internal energy, and gravitational forces take over. However, the star's contraction leads to an increase in internal temperature and pressure, which ultimately results in the resumption of thermonuclear reactions. But now they occur in the hydrogen shell surrounding the helium core. From this moment, the star enters the subgiant stage, although externally this may be almost imperceptible. The burning of hydrogen in the shell leads to the formation of an increasing amount of helium, which gradually, under the influence of convective currents, sinks to the core, increasing its size and mass. Simultaneously, the hydrogen shell begins to expand, continuing to generate an enormous amount of energy, even more than during fusion in the core. The increase in energy generation leads to a rise in luminosity, and the star begins to expand, increasing in size by 2 to 10 times. During expansion, the gas cools, which leads to a decrease in temperature within the star's interior and a shift in its color towards the red end of the spectrum. Therefore, at the subgiant stage, stars less massive than the Sun acquire an orange hue and have a surface temperature of about 5,000 Kelvin. It is curious that, despite the overall cooling during expansion, the star significantly increases its luminosity. This is explained by the simple geometric relationship between surface area and radius, 4 pi r superscript 2. Since the radius is squared, doubling the radius leads to a 4-fold increase in surface area. Accordingly, if the radius increases by 10 times, the star will emit 100 times more energy at an unchanged surface temperature. Of course, the temperature does not remain constant and actually decreases, so the actual increase in brightness is somewhat less, but still remains very significant. The further evolution of a star largely depends on its mass and metallicity. Stars with a mass between 20% and 60% of the Sun's mass can remain in the subgiant stage for up to 8 billion years, continuing to burn hydrogen in the shell and accumulate helium in the core. Gradually, the helium core increases in mass so much that it contracts and becomes degenerate, meaning the matter can no longer be compressed further. This compression is accompanied by a rise in temperature, which, in turn, accelerates thermonuclear fusion in the hydrogen shell. As a result, even more energy is produced, and the star continues to expand and redden, transforming into a red giant. On the HR diagram, the star moves to the red giant branch, where most stars of this type are found. Examples of such stars are the famous Aldebaran and Arcturus, inflated balls of plasma, possessing enormous luminosity due to their large surface area, but having a relatively low surface temperature, 3 to 4,000 Kelvin. When stars less massive than the Sun reach the peak of their evolution as a red giant, they shed their outer layers, forming spectacular planetary nebulae and a hot helium-white dwarf. Completely different processes occur with stars having a mass between 0.6 and 2 solar masses, which includes our Sun. Similar to less massive stars, they accumulate helium in their cores until their hydrogen reserves are exhausted. Then they begin to contract, and their temperature and luminosity increase, even without thermonuclear fusion. In this state, a star can remain for several million years until the core becomes hot enough to initiate hydrogen burning around it. This reaction stabilizes the temperature and luminosity, and the star begins to expand and cool. In general, For stars of similar mass, this stage of the evolutionary path marks the end of their main sequence lifetime, and the beginning of the period when the star transforms into a giant. Once a critical mass accumulates in the core, it undergoes colossal compression until the pressure reaches the point of degeneracy, and the temperature sharply rises. From this moment, the star transforms into a red giant, significantly increasing in size. Our Sun, when it enters this phase, will become so enormous that the planets closest to it, such as Mercury and Venus, will not survive. In the course of further evolution, the Sun in its red giant phase could swell to a radius 256 times its current size. This corresponds to 1.2 astronomical units, which is larger than Earth's current orbital radius. Computer modeling shows that in those distant times, our planet's orbit will undergo changes and shift to a distance 1.5 times greater than its current one. However, other models, taking tidal effects into account, predict a somewhat smaller orbital radius for Earth. Thus, it is highly probable that our planet will ultimately not escape the fate of Mercury and Venus. But for our star, not all is predetermined yet. Even at this stage, the Sun will still be able to fight for its existence. The fact is that for stars similar to the Sun in mass, the core, upon contraction, is capable of heating up to a temperature of 100 million Kelvin. This is the critical threshold at which helium nuclei begin the fusion process, meaning helium burning starts in the star's core, forming carbon. Moreover, this fusion begins very rapidly and involves a large amount of helium at once, which is why the process is called the helium flash. The fusion of helium occurs through a process known as the triple alpha cycle. This is a kind of bridge connecting the proton-proton cycle and the C-nose cycle. Why triple and why alpha? Alpha particles are helium nuclei. It all begins with two helium nuclei that fuse, forming an unstable beryllium-8 nucleus. Almost instantaneously, in negligible fractions of a second, the beryllium nucleus combines with another helium nucleus, the third one, forming a carbon nucleus. This is how the triple alpha cycle occurs. It is important to note that in both stages of this reaction, photons are released in the gamma range, similar to what happens during the proton-proton cycle. Thus, this is another source of energy for the star. So, essentially, the star gains two energy sources at once, from hydrogen burning in the hydrogen shell and from helium burning in the core. It becomes a kind of double thermonuclear reactor. It might seem that with such an amount of energy, the star should expand greatly. However, surprisingly, this does not happen. The energy released during the helium flash is used to overcome degeneracy in the core and to initiate convection. Therefore, the star, on the contrary, loses some brightness, but remains many times brighter than the Sun. At the same time, it becomes slightly hotter than most red giants, with a surface temperature of about 5,000 Kelvin. On the Hertzsprung-Russell diagram, it looks like this. From the inflated red giant stage, the star moves to the so-called horizontal branch, where brightness is lower and temperature is higher. This stage of evolution for the Sun and similar stars is significantly shorter than the main sequence phase, lasting about 100 million years. During this time, helium fusion continues in the core, and carbon, as well as oxygen, gradually accumulate. Sooner or later, the helium runs out, and the core turns into a ball of carbon. Fusion ceases, and the equilibrium between gravity and radiation is again disturbed. The star begins to contract again, and its temperature rises. Since there is still a lot of hydrogen and helium outside the core, the contraction leads to the ignition of helium in a shell around the carbon core, as well as hydrogen fusion in a second shell surrounding the helium one. And it is at this time, when the star has two active shells, that such an enormous amount of energy is released that it expands again, transforming this time into a supergiant. A well-known example of such a star is Antares, whose luminosity is 13,000 times that of the Sun. This phase of evolution is called the asymptotic giant branch, AGB, and it is the last bright flash of a medium-mass star. After both shells exhaust their fuel, its life cycle comes to an end. At this stage, stellar winds blow much stronger than in the modern Sun, so the star loses more and more matter into space even before fusion in its interior ceases. A significant amount of ejected gas from its envelope already forms around the supergiant. Ultimately, after all reactions cease, the outer envelope is completely shed, leaving behind a hot carbon-oxygen core, or white dwarf. It is still hot enough to emit high-energy ultraviolet photons, which, in turn, ionize the surrounding gas cloud that continues to expand. This entire spectacular, bright, shining bubble is called a planetary nebula. Of course, this name has nothing to do with planets and their evolution. William Herschel believed they were the nurseries of star systems where planets are born. In reality, he was observing their end, but the name has stuck since then. An impressive example of stellar death is the V838 Monocerotis system. From 2002 to 2006, astronomers used the Hubble Space Telescope to observe, in real time, a star shedding its outer layers, a truly cosmic spectacle. Now, let's turn our attention to stars significantly larger and more massive than our Sun. The final stages of their lives are a captivating display of cosmic transformations. We'll begin with stars that are at least 8 times the mass of the Sun. These cosmic giants skip the subgiant phase, instead starting their lives as white or blue giants. Once the hydrogen in their core is depleted, nuclear reactions don't cease. The core, bypassing a degenerate state, immediately begins burning helium. As helium fusion marks the twilight of the star's life, its color shifts from blue or blue-white to orange, and its surface temperature drops from tens of thousands of Kelvin to a more modest 4,000 to 5,000 Kelvin. Simultaneously, the star's size dramatically increases, classifying it as a supergiant. O-class stars, with colossal masses exceeding 16 times that of the Sun, swell to incredible sizes, surpassing the upper limit for giants, and instantly become red supergiants. However, such stars are quite rare, as the frequency of cosmic objects is inversely proportional to their mass. The most intriguing metamorphoses occur in stars with masses more than 8 times that of the Sun. After exhausting the helium in their core, they retain enough mass to continue synthesizing elements beyond carbon. Reactions involve silicon, magnesium, and other elements, up to iron. Each new reaction begins at the core, pushing lighter elements towards the periphery, resulting in a multi-layered, onion-like structure. It's important to note that most chemical elements in the universe, up to iron, originated through nucleosynthesis within the cores of such stars. An iron atom's nucleus possesses the highest binding energy per nucleon, meaning any nuclear reactions involving iron, whether fission or fusion, require energy absorption. Consequently, iron cannot serve as fuel for further nuclear reactions and accumulates in the massive star's core. Meanwhile, the temperature and pressure in the star's core continue to rise, reaching a critical point where electrons are forced into protons, forming neutrons. Of course, from a quantum physics perspective, this process is far from our everyday understanding. Protons and electrons, so to speak, possess a certain malleability, and readily merge into a single particle. However, the challenge lies in bringing them close enough to a critical distance. In this process, immense pressure plays a key role, as does the high temperature of the plasma where electrons are stripped from the nucleus. The fusion of a proton and an electron happens almost instantaneously and involves an immense number of atoms. As a result, the core of the massive star, which once surpassed some small stars in size, transforms within seconds into a small sphere of neutrons, merely a few tens of kilometers in diameter. This compression creates a void in the star's center, which can no longer support the upper layers, causing the entire star to begin collapsing. The star's outer envelope crashes down onto the remaining core, moving at a significant fraction of the speed of light. Matter collides with the dense neutron core at immense velocities. The energy released is so vast that the star explodes, generating a Type II supernova. At this moment, an amount of energy equivalent to the radiation of hundreds of billions of ordinary stars is unleashed, allowing the supernova to outshine an entire galaxy. Other types of supernovae exist and will be discussed later. Despite the colossal energy of the explosion, the star is not entirely destroyed. If its mass exceeded 8 solar masses, a neutron core remains after the blast, classified as a neutron star. Along with black holes, neutron stars are objects of minimal size and maximal density. Typically, their radius is about 10 kilometers, and their mass starts from 1.4 solar masses, the Chandrasekhar limit. The question of a neutron star's upper mass limit remains a subject of debate, as various theoretical models yield results ranging from 1.8 to 3.5 solar masses. Within neutron stars, where matter reaches incredible density, thermonuclear reactions cease due to the absence of necessary elements. As a result, these cosmic bodies slowly cool, like the dying embers of a universal bonfire. However, despite this, neutron stars continue to evolve, interacting with other cosmic objects. Collisions with asteroids and comets, as well as the accretion of matter from a companion star in a binary system, can alter their structure and characteristics. Neutron stars derive their name from the predominance of neutrons in their composition, as supported by most modern models. These astonishing objects are prevented from further collapse by neutron degeneracy pressure, similar to how white dwarfs resist compression due to electron degeneracy pressure. In addition to degeneracy pressure, more massive neutron stars utilize nuclear forces to combat gravity. However, calculations show that gravitational attraction overcomes all forces when a neutron star's mass exceeds the Tolman-Oppenheimer-Volkoff (TOV) limit. This limit, which depends on the star's chemical composition, ranges from 2.2 to nearly 3 solar masses. The most massive known neutron star has a mass of approximately 2.35 solar masses. If an object's mass surpasses this limit, it inevitably collapses into a black hole. Thus, the Oppenheimer-Volkoff limit serves as the lower mass boundary for black holes. Nevertheless, the lightest known black hole has a mass 3.8 times that of the Sun, which casts doubt on the accuracy of current calculations. Young neutron stars, freshly formed, can have surface temperatures reaching tens of millions of Kelvin. However, lacking internal energy sources, they gradually cool down. For instance, the surface temperature of one well-studied neutron star averages 434,000 Kelvin. In comparison, the Sun's surface temperature is 5,780 Kelvin. But the primary characteristic of neutron stars is their incredible density. A teaspoon of matter from such a star weighs several billion tons, comparable to a small mountain. Besides density, neutron stars are astonishing for their rotation speed. Just as a figure skater pulls their arms in to increase their spin, a neutron star, shrinking during formation, increases its rotation speed in accordance with the law of conservation of angular momentum. Young neutron stars can rotate at speeds of several hundred revolutions per second. The fastest known neutron star spins at 716 revolutions per second, which is 43,000 revolutions per minute. Some neutron stars emit narrow beams of electromagnetic waves whose axis does not align with their rotation axis. These objects are called pulsars. If a pulsar's emission beam is directed towards Earth, we can observe periodic signals. It is estimated that there are about 1 billion neutron stars in our galaxy. However, many of them have long since cooled, and their electromagnetic radiation has become faint. Therefore, most known neutron stars have been detected in specific situations, such as when they are pulsars or part of a binary system. Similar to neutron stars, black holes are also difficult to detect. Their detection relies on their gravitational influence on surrounding matter and the electromagnetic radiation, such as visible light, emitted by that matter. With that, we can pause here, as there's much more fascinating information about stellar evolution ahead, particularly regarding how stars interact in binary and multi-star systems.